Okay. Later on, we'll look at a simple example, so you can become familiar with this logic before we go over the algorithm for verification and debugging. There are three types of real-time logic constraints, constants. These are actions. These are schedulable units of work. So if this is a computer system, that means a task, a process, a thread. Okay, that is a schedulable unit of work. But these actions could be real actions. So this could be a robot arm moving from left to right. It could be the railroad crossing gate going up or going down. It could be a valve in a pipe closing or opening. So those are schedulable units of work. Now, events constants are temporal markers, and these are instantaneous. External event is indicated by omega. So, for example, I can have an external event of me pressing this arrow button. Okay, that's an external event. So I'm external to this laptop. Start event means the beginning. Okay, it marks the beginning of an action. Or, for example, I have the start event of the gate arm starting to move up or maybe move down. And this down arrow indicates the end event, the stop event of an action. So the gate is completely moved down. So that I can model this interval of time later on. And integers are used for timing constraints, for all the notations of time here. And the reason is because if we have real numbers, there will be a problem. And I'll be happy to discuss the reason why. Okay, so this is an example railroad crossing. So I come from Houston, Texas, and there are lots of railroad crossings, intersection. And in Texas, people drive fast. Okay, and sometimes they ignore signs and traffic light. That's why we install intersection cameras to catch people who run a red light. So here we light the gate. So basically you have cars here. Okay, and we light the gate to be completely moved down before the train, indicated by this darker green rectangle, arrive at the intersection. So here there's a small sensor that detects the approach of a train. So once the train is detected by the sensor, then it sends a signal to the gate controller, which is going to lower the gate. Okay, so we light the gate to be completely down before the train arrives at the crossing, because if not, the car may try to continue, beat the intersection. Okay, car arrives. Car moving forward. Okay, the train is coming. So these events are happening simultaneously. We cannot use a regular temporal logic to model this, because typically it uses the interleaving model of computation. Temporal logic was used for concurrent to model concurrent systems, concurrent processes. But real-time logic allows you to specify all this happening simultaneously or in parallel. Okay, car passes. Okay, the train is coming. Okay, and the gate is down. Okay, gate is down. Okay, so if there are more cars coming, they cannot go through and the train goes through. After the train crosses the crossing, then the gate can start moving up. So that's the scenario we like to specify. It's a very simple system, but it's good for lecture, presentation, discussion. Okay, so gate moves up. And you see this the timing constraint or the timing performance or behavior here. So it takes 45 seconds for the train to reach the crossing from the sensor, and it takes 60 seconds. So there are only a few cars, so it takes 60 seconds for the train to pass. Okay? So now we're going to model this in real-time logic. Okay? So here is what we are going to say. When the train approaches the sensor, a signal will initiate the lowering of the gate, and the gate is moved down to the position within 30 seconds and from being detected by the sensor, because it takes 45 seconds for the train to arrive. So 30 seconds, we have a 15 seconds buffer zone. So the gate will be completely down before the train arrives. So this is specified in real-time logic. Okay, you see, the less than or equal is because all these real-time logic indicates integer time. So here, train approach is the occurrence time of the train approach, the x occurrence of that x instance, is less than or equal. So that means at or before the start of the gate moving down. So when a train is detected, then the gate is going to start moving down. It could be a little bit later. That's less than or equal. It's going to indicate that. And notice that this is an N. So, and also the down gate. Okay, the end of the down gate is going to occur less than or equal to the time the train approach happens plus 30. Okay, so the 30 is a deadline for basically the occurrence time of the gate completely moving down, and this is captured in this real-time logic statement. Okay, now the gate takes 15 seconds to lower itself, and this comes from the performance of this particular motor, driving this gate from the up to the down position. Okay, so this is considered a delay or computation time. Okay, this is something that again is dependent on the actual gate controller and the gate and the weather. Okay, so this is specified, as you can see, the integer is on the left. Okay, and that usually indicates delay or computation time. And you see down gate here and down gate here. And this is a down arrow, and this is up arrow. So we are really relating the two endpoints, the beginning and the end point of the same action. And this tells you the computation time. So very complex system can also be specified. You just have a lot of RTL formulas. Now, the next thing we like to say is if the train needs at least 45 seconds to go from the sensor to the crossing, and the train crossing is completed within 60 seconds, from being detected by the sensor, then we are guaranteed that at the start of the train crossing, the gate has moved down. And that the train leaves the crossing within 45 seconds from the time the gate has been completely has been completely moved down. So this is captured by this statement in RTL. Okay? So you see this is a, if this happened, then this is going to happen. So this is really the safety assertion, and we like to relate this safety assertion with the specification, which will capture here. Okay? A very simple system, but I think it illustrates what we are trying to do here. Questions so far? Okay. So now the class of formulas that are in this format is called Path-RTL. It's a subclass of RTL. Because by now, the theorists in the audience will say, okay, this is first-order logic is not decidable. So how can we claim to have an efficient solution? But this is only a subclass of the RTL formulas. And for this, we can have an efficient solution. Notice that all these statements have basically an occurrence function plus or minus an integer less than or equal to another occurrence function. And they are connected with connectives like AND. And of course, basic logic course will tell you that this imply can be changed, right? So it becomes not the premise or the consequence. So it can be changed to logical connectives other than the implied symbol, right? But you can see, all this, okay, have the occurrence function plus or minus. Here in this case is a 0, integer is 0. Less than or equal to another occurrence function. So if your formulas are of this form, then they are called Path-RTL. And for this, we can come up with a general algorithm. Now, in the worst case, this is still exponential time, and hence, the objective of this talk is to basically push the envelope by saying that, in fact, a lot of these formulas can be analyzed in polynomial time. Okay, so this is the form, as I said, the form of the formulas. Occurrence function plus or minus integer less than or equal to another occurrence function. Now, we have analyzed several Brio systems, including railroad crossing. Well, the system I have is very small, but there could be multiple tracks. Okay. We have analyzed a nuclear reactor, Boeing 77, the